All right, hey everybody. Okay, so last time we developed the solution to x dot equals ax in terms of the geometry of the A matrix, namely the decomposition into eigenvalues and eigenvectors. So just remember last time, if we have a system x dot equals matrix A times x, then our solution is going to be x at time t is the matrix of eigenvectors, big T, e to the diagonal matrix times time, times t inverse x naught. Okay, so T is a matrix of eigenvectors, D is a matrix of eigenvalues of A. So remember we have A equals T, D, T inverse. Okay, that's what we did last time. And so this time what we're going to do is start looking at specific A matrices, specific ODEs, and thinking about what their behavior looks like. Okay, so we're going to tie this back to physical systems, how to actually draw pictures. This is going to be kind of a more, I hope, fun and interesting lecture where we really draw some pictures and get an understanding of the physics of what's happening. Okay? And probably we won't get to this in this lecture, but on Wednesday what we're going to do is look at if you have a nonlinear differential equation, x dot equals some function of x. Okay, these are all vectors, so this is next time. Then what we're going to do is look for fixed points where f is 0, and we're going to linearize. We're going to linearize around those fixed points to get a system x dot equals ax. Okay, so linear differential equations like x dot equals a times x are not only useful for really boring, simple linear systems. You can also use them for extremely complicated nonlinear systems like fluid flows, gravitational potentials, earthquake modeling, pretty much anything that's really nonlinear. You can often find some state to linearize about, and you can analyze its linear stability and get an idea of what the system's going to do. Okay, so that's where we're going. Are there any questions before I move on to the actual material for today? About last week's lecture? No? Before I start, I should probably give you just a couple of tips on the homework, because I think there was a little bit of confusion. So homework tips, let's see, what is a tip for the homework? In the first problem I said something like, f of t equals e to the I t, and I told you to write down analytically the real and the imaginary part. Okay? I'm not looking for anything complicated. You don't need to do a Taylor series or anything fancy. You're just trying to say this is equal to cos t plus I sine t. That is an analytic expression for the real part and the imaginary part. And if I ask you to plot them, I just mean plot cos of t and sine of t. So for example, we have the real part and the imaginary part. So something like that would be fine in MATLAB. Okay? That's what I mean by analytic expression. I just mean write it down. Don't just simulate it. Okay? In the last problem, I give you a Lagrangian, and I ask you to take a bunch of partial derivatives. So I should probably remind you exactly how to do that. So if I have some function x, some function of both x and the time derivative of x, maybe this is x dot squared plus cos of x. How would I take the partial of f with respect to x? Yeah, just forget the x dot term. That's not a variable with respect to x as far as I'm concerned. That's like a constant. So that derivative with respect to x is partial is 0. And I just get minus sine of x. And what's the partial of f with respect to x dot? Yeah, same thing, except I forget this term. There's no partial of x with respect to x dot. They're different kind of independent variables. with respect to partial derivatives. So I get 2x dot. Okay, pretty simple stuff, but I don't want anyone to be like confused and bang their head against a wall on the homework. That's what I mean by partials. That's what I mean by writing analytic complex parts. And in the next lecture, when we do linearization, you'll get everything you need to linearize the pendulum system that you get from the Euler-Lagrange equations. Okay, so if you don't quite know how to linearize that system yet, that's all that we're going to do in the Wednesday lecture. Okay. Okay, good. So for today, we're going to do examples of x dot equals ax. So the first example, how many of you actually download the lecture notes before lecture? I'm just curious how many of you are following on. Okay, that's fine. I just want to make sure that it's not super boring and I'm just saying the same thing that you're seeing. Yeah?
Is there any way to define that exponent term in MATLAB?
E to the dt? Yeah, so this is nice in MATLAB. Okay, so in MATLAB, that's a good question. How do I actually make this matrix exponential in MATLAB? So the first line would be TD equals eig of A. Okay, now I have a matrix of eigenvectors, a matrix of diagonal eigenvalues. So D is a matrix, only lambdas on the diagonal, zeros everywhere else. So what I would do is I would say little d equals the diag of big D. Okay, so the diag command, if I give diag a matrix, it will give me a vector of just the diagonal elements. And if I give it a vector, it will give me a matrix with that vector on the diagonal. So it takes two different arguments. If I give it a matrix, it'll give me just a vector of the diagonal elements. Then what I would say is like e to the d equals exp of d. And if there was a time in here, I'd say exp of d times t. And what that's going to do, okay, so this one is going to take my big matrix, lambda 1, lambda 2, dot, dot, dot. And it's going to give me a vector, lambda 1, lambda 2, dot, 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 lambda n. That's what this first diag does. Then when I say e to the d equals exp of d times t, if I give it a vector, it knows that I just need the exponential of each term, term-wise. So this is going to give me e to the lambda 1t, e to the lambda 2t, dot, 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 in a vector. And remember, d is a vector of numbers, t is a number, this is a vector of numbers. Okay, it's not an analytic expression. These are numbers in here. And then finally, I say e to the big D equals diag of e to the little d. Okay, so now when I give a vector to diag, it'll turn it into a big matrix with that vector on the diagonal. So this is going to give me a big matrix e to the lambda 1t, e to the lambda 2t, dot, 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 zeros everywhere else. Does that make sense? So diag, if I give it a matrix, it pulls out the diagonals into a vector. If I give it a vector, it turns that vector into the diagonal of a new matrix with zeros everywhere else. So these are the 4 commands in MATLAB to actually compute this thing. Yeah?
Pretty sure that exponential function will just do a termwise for a matrix too. Yeah.
That's a good point. Okay, so that's a really, really good point. So what we could do, yeah, I feel stupid. So this is a lot simpler. What we could do is just say e to the d equals exp of d. That's right. Because if I just give exp a matrix or an array or a vector, it will always take the exponential of every single element of that. Now, if you do this, you have to be a little careful. because we're assuming that D is diagonal. We know D is diagonal, and so we know that e to the diagonal is a diagonal of e to each of those elements. And so that's why we can just take the exponential of each of those elements times t. Yeah, that's a really good point. So you can just do this e to the dt. It's good to know how to manipulate the diag command. We'll use it later in the class also.
Would that give you ones where the zeros are, though?
I'm sorry?
Would that give you ones where the zeros are, though?
E to the 0, yeah, probably would. Okay. That's right. Okay, so don't do this. Because, does this make sense to everyone? If I have D equals some number, D1, D2, dot, 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 with zeros. If I take e to those zeros, they become ones. So if you did this, you would have to manually make all of those 0, and we don't want to do that. Okay, so what I wrote down originally is the right way to do this, apparently. Thank you. But it's good to know. So it's good to know what MATLAB does when you give it a matrix. Most of the time it does that operation to each of those matrix elements. Okay, sorry, that was a little bit confusing. But does anyone have any other questions to deconfuse or more confuse me? Yeah?
Not related to MATLAB, but for the the reason it's not sin x dot by the chain rule? Or
Yeah, so the partial derivative assumes that x dot and x can vary independently.
so you don't have to apply the chain rule when you
No, so you don't apply the chain rule. No. Yeah. Okay, so in MATLAB, if you wanted to compute this, you would find the eigenvectors and eigenvalues. You would pull out the diagonal elements of that D matrix into a column little d. You'd take e to the little d times time. That's now another column vector. And then you would turn that column vector into a matrix with those terms on the diagonal and zeros everywhere else. Okay, that's e to the dt. Okay, let's do some examples. Okay, so last time we had x dot, so I'm going to write this as d dt of some variable x and v. It doesn't matter what I call these are just variables, right? I'm thinking of it as position and velocity, but you can think of it as whatever. This is going to equal the matrix 3, minus 1, minus 1, 3 times xv. Okay, so this was the A matrix that we used in the last lecture to compute eigenvalues and eigenvectors. So we know what they are. We know that t is 1, 1, 1, minus 1. Remember, this was one of the eigenvectors, the column 1, 1. And the other eigenvector was 1, minus 1. D is, I think, a diagonal with 2 and 4. Okay, this is just from the last lecture. And the only other thing that we need to write the solution of this is t inverse, right? Okay, so we're just going to do the inverse really quickly. Whenever I have to do an inverse of a 2 by 2 matrix, I just do it by hand. So to do it by hand, we write that matrix T next to the identity matrix. And then I'm going to row reduce the matrix on the left until it looks like the identity. And I'm going to do all of the same things to this matrix on the right. And whatever I get over here is T inverse. Okay? So I'm going to subtract the first row from the second and get 0, minus 2, minus 1, 1. Then I'm going to divide the second row by a negative 2. So I'm going to get 1, 1, 1, 0, 0, 1, 1 half, minus 1 half. And then finally, I'm going to subtract the second row from the first row. This is all in the lecture notes. So the bottom row doesn't change now. But the top row, I've subtracted the bottom row from the top row, so I get 1/2, 1/2. Now, this matrix on the left that used to be T is the identity, and this is T inverse. Okay, so T inverse is 1/2, 1/2, 1/2, minus 1/2. And good, that's right. Yeah.
T matrix is the eigenvectors now.
The columns of T are eigenvectors corresponding to 2 and 4.
So can you change the columns? For example, write the second one first.
Okay, so if you wanted to swap the columns of T, you certainly could do that, but you would have to swap the elements of D. So the first eigenvector in T has to correspond to the first eigenvalue in D. The second column of T has to correspond to the second value of D. That's a really good question. You basically have as much freedom as you want to change the order of these elements as long as you swap the columns of T accordingly. It should totally work out.
Why would you have to switch the
Maybe, I was doing this matrix and I just stumbled upon lambda 4 first. And so I just wrote lambda, maybe I'm just doing this in order and I find the eigenvector corresponding to lambda 4, then lambda 2. That's totally fine, as long as you get the order right for both parts. Right, so every eigenvector is always paired to an eigenvalue. Yeah, really good questions. Okay, I'm going to erase this algebra here. It really doesn't matter. We could program our computer to do it. It's expensive. So you could check pretty easily in MATLAB that if I take T times D times T inverse, this really does exactly equal A. It's like easy to do in MATLAB. Okay, so what is the solution of this differential equation? So x at time t and v at time t equal what? Yeah, it equals t times e to the diagonal t times t inverse. So t is 1, 1, 1, minus 1. E to the diagonal t is pretty simple. It's just e to the 2t, 0, 0, e to the 4t. And then t inverse is 0.5, 0.5, 0.5, minus 0.5. Right? I'm going to do this out long ways. It's kind of a pain, but I just want you to really see where all this comes from. You can actually get the full solution by writing this out. Okay, so this equals, so first I'm just going to multiply these two matrices. Okay, I get 1/2 e to the 2t, and then I get 1/2 e to the 4t. Okay, then I get 1/2 e to the 2t, pretty simple. And minus 1/2 e to the 4t. Okay, I'm just by hand multiplying these two matrices. Now I'm going to multiply their product by t. Ooh, one got away from me. All right. Probably don't need this. All right. So in the first entry, we have 1/2 e to the 2t and 1/2 e to the 4t. So everything has a 1/2. I'm just going to pop the 1/2 out front. So I get e to the 2t plus e to the 4t. Then I get e to the 2t minus e to the 4t. Then I get e to the 2t minus e to the 4t. And finally, I get e to the 2t minus minus is plus e to the 4t. And remember, this is all times x naught, v naught. Each of these should have an x naught, v naught, x naught, v naught. Initial conditions. Okay. Questions? I mean, it's kind of like nasty algebra, but all I do to get the solution of x and t at any time I want in the future, arbitrary times, is I take t times e to the dt times t. Done. Okay? And you can actually do it by hand, and this expression's really not that bad. Okay? It means that x has some terms multiplying x naught and v naught, and both of those terms are going to grow exponentially with a factor of e to the 2t and e to the 4t. Okay? Any questions about this? You can do this for any matrix, any 2 by 2 matrix, any 3 by 3 matrix. It totally works for everything, basically. Okay, so I'm going to draw the phase portrait. This should be kind of neat. So what I think is really, really useful about this geometric interpretation of differential equations is that we can sketch the solutions really easily. And in my professional career, I've only written out the full solution to a differential equation like this maybe 6 times. A few times when I was taking classes and a few times when I was teaching classes. You don't really do this very much. Okay, that number is going to double in the next 2 lectures, but you really don't do that that much. What you usually do is you think geometrically. Okay? So I can write the xv plane. This is my phase portrait. Okay, this has my position and my velocity. And what I'm going to do is essentially, last time we recognized that if we have eigenvectors of A, then if I multiply A by that eigenvector, everything stays in that eigenvector. Or if I multiply e to the at by that eigenvector, everything stays in that eigenvector. You should verify this. If I take e to the a, okay, so A times my eigenvector is equal to lambda times my eigenvector. If I take e to the at times my eigenvector, it also stays in the same direction as my eigenvector, because e to the at is made up of a sum of a's. Identity plus a squared plus a cubed, and so on and so forth, right? That Taylor series we wrote down. So this equals e to the lambda t in the same direction of xc. So my dynamics, if I started with an initial condition in xc, so if x naught was in the xc direction, my solution would always stay in that xc direction. So for this system, we had xc1 in the 1, 1 direction, and we had xc2 in the 1, minus 1 direction. Those were our eigenvectors. Now, you should really verify this. You can do this using the Taylor series. You can do the T inverse factorization, whatever you want. But if I start with an initial condition in the xc1 direction, my point will always stay in that direction. It will never gain anything in the xc2 direction. And the same thing in xc2. If my x naught, v naught are in this direction, anywhere along this blue line, my solution will always stay on that blue line. It's called an invariant manifold because it never changes with the dynamics. Okay? So what were the eigenvalues corresponding to my red line here? Two, right? This is lambda equals 2. Okay, that's a positive eigenvalue. That's unstable. So e to the 2t gets bigger and bigger and bigger as t gets bigger. So particles along this line move away from the origin. X and v grow in time. Now, what about the xc2 direction? What's that eigenvalue? 4. Okay, so 4 is even larger positive. So things are moving faster in the blue direction, right? So if I start in the blue direction, if I start a little particle right here, it's going to flee from the origin at a great rate, at an exponential rate. It's going to move away from the origin. Okay? So remember, I haven't done anything with the actual solution. I haven't plugged any numbers into here. I'm just doing geometrically what I think should happen from T and D. Okay, I looked at my A matrix. I computed its eigenvectors and eigenvalues. And I can draw on this phase portrait the invariant manifolds or the invariant subspaces defined by those eigenvectors. And so finally what I can do is I can start drawing some test particles here. So if I start with a little test particle here, what it's going to do is it's going to move both in the C2 and the C1 directions because it's got a little bit of both. And it's going to start moving in the C1 direction, and then it's going to accelerate into the C2 direction because this is faster. Okay, so you get these kind of quadratic looking trajectories. If I started over here, I'd have the same thing. If I started out here, it would be the same thing. If I started on the other side of C1, so I had kind of a negative component of this blue curve, that negative component is going to grow to negative infinity. I get the same thing back here. Okay, so those black lines are actually the solutions. This is kind of a sketch of the solutions of any initial condition you want. So if you dropped a point anywhere, like let's say I dropped a point right here, it would pass through that curve. Mathematically, numerically in a computer, you would actually compute t times e to the dt times t inverse to figure out exactly where your particle goes. But a lot of times all we care about is what is the shape of the system near the origin. This is an unstable system. Any point that you can name near the origin is going to go away from the origin unless it's exactly at x equals v equals 0. So this is called a phase portrait. This is a really, really useful tool in engineering to plot the solution of ODEs. I didn't have to write down the solution at all. I just had to know the eigenvectors and the eigenvalues, and that my system was linear. Okay, that was a little fast. Are there questions?
That eigenvalue of C2, that's 2 times bigger than the other one.
It's 2 times bigger than the other one, yeah.
Why is beginning of the function like this? I think there are 2 vectors, which this one is double that, so we have to start that way.
Yeah, so if you plot a line versus a parabola, so this is kind of like a slope 1, and this is like a slope lambda equals 2. So that's kind of like lambda equals 2 and lambda equals 4. This is an analogy. So for x less than 1, the line is actually larger than the parabola. It's above the parabola. And so the smaller eigenvalue actually grows faster for small times. But then once it passes, maybe I should call this time, then once it passes some critical point, then the higher value of lambda will be much, much larger, much, much faster, and so it'll accelerate into the C2 direction and eventually be much faster in C2. So it's a little funny. It's a really good question. It essentially has to do with this picture. This is just a cartoon. Yeah.
So this plot, you're getting exact information from it? I mean, if you have that one line, if you started with, say, velocity 1 meter per second, at some future time, would you have position 2 meters per second? Exactly?
So if I started exactly at 1, 1 here, so if it was at initial condition x naught equals 1 meter, v equals 1 meter per second, then I would know that after 1 second, I would be at e meters, and I'd be moving at e meters per second. Sorry, e squared, e to the 2t.
But it does mean that x and v will be equal.
Yeah, if I start on this line, x and v will always remain equal. If I start on this line, x and v will always remain equal and opposite, always. Yeah. They're exponential, yeah. Okay, let's do some more examples. Hopefully this will become more clear, okay? Okay, so another example that I like to do, this one's a little simpler, is d dt of x and v equals 1, 0, minus 1, 0, x and v. Okay, so what's the solution to this differential equation? Anyone? Anyone at all? Yeah. It's already diagonal, so I don't really need to do any eigenvector decomposition. It's just going to be e to the t, and then e to the minus t, and then zeros off diagonal. That's the solution. We know the solution. Okay? If I ran this through MATLAB, I would find that t equals 1, 0, 0, 1. So t is the identity matrix, right? One eigenvector is in the x direction, one eigenvector is in the y direction. And I would get that d equals plus 1 and minus 1. Pretty simple, okay? So the way that we're going to write this is, let's see what colors I use. Okay, so we have this direction, e to the minus t is stable, right? As t goes to infinity, e to the minus t goes to 0. So this direction is stable. E to the plus t is unstable. So what this system does is, in the x direction, it's unstable. My x initial condition is going to grow and grow and grow to infinity. So the x component is going to get infinitely large, while the v component is actually shrinking down to 0. It's stable in the v direction. So I can draw my phase portrait just like before. Okay, so this is x and v, except now the v direction is my second eigenvector, and my x direction is my first eigenvector, and it's stable in v, and it's unstable in x. So if I start with a little point here, it's going to move in towards the origin in the v direction. And as it does that, it's going to grow to infinity in the x direction. So it's going to look like that. Same thing for down here. The v part of this is going to go to 0. And then the x part is going to go to infinity. And I can just draw this, keep going. Okay, so this is called a saddle point. I can tell you why it's called a saddle point in a minute. But the basic idea is that it's got at least one stable direction and at least one unstable direction. So every trajectory that I can name, if I just randomly pick an initial condition, it's almost certainly going to go to either positive or negative infinity in x and go to 0 in v. The only exceptions is if I picked an initial condition exactly on the vx axis, then it's going to go to the origin. Okay? This is called a saddle point because you could derive these equations from a potential well that looked like a saddle. So how do I draw this? You can picture what a saddle looks like. You put on your horse, you sit on a saddle. It's got, I'm really bad at drawing saddles. So it's got, this is where your legs go on either side of this, right? Your butt goes here, front goes there. And then that's where your legs go, on the left and the right. Okay, so this is a saddle. Now you can imagine if I drop a bead somewhere on this saddle, right? If I dropped it exactly on the ridge of the saddle, it's actually stable, and it's going to come to rest right at the bottom. That's the v direction. But if I tip it a teeny bit in either the plus or minus x direction, it's going to roll off into this infinite negative potential well. Okay? That's why it's called a saddle, because it looks like a saddle. Okay? They were really creative when they named all of these things. This is a saddle. This is called a source, because it's a source. It goes to infinity. It infinitely grows. Okay, questions about this saddle point? What we're doing here, this is not just like cartoons, right? My kid draws with crayons, I draw with markers. This is not just a cartoon. These are the building blocks of all differential equations, okay? I can have a saddle in a 5-dimensional system as long as I have one unstable direction and one stable direction, okay? You can build the solution to any differential equation you want out of saddles and sources and the other things that I'm going to tell you about today and tomorrow, okay? And these generalize to higher dimensions, yeah. These absolutely show up in real systems. Yeah, I mean, so this is a real system. I could literally take a bead and drop it on a saddle and it would roll, and the dynamics would be given by this linearly. A better example of a saddle, we see saddles all the time. Let's think of a good one. Okay, so you have the sun and you have Jupiter, not to scale. And here's the dashed line, which is the axis between them. And I'm going to take the equations of motion and rotate them so that this axis always stays fixed. And so that 0 is always at the center of mass. Okay? You can do this. You can write down the equations of motion for this 2-body problem in a rotating frame with the origin equal to the center of mass of the system. So there are so this is a nonlinear differential equation. This is given by, if I have some particle in here, some little, let's say you're in a spaceship and you're floating around this gravitational potential, or you're an asteroid and you have some initial position x and some initial velocity v, then you're going to have 3 positions, right, x, y, and z, and you're going to have 3 velocities, ux, uy, uv. And the derivative of that, ddt of my position and velocity, is going to equal essentially F equals ma. So there's some force which is proportional to where I am in this gravitational potential. It's nonlinear, right? Gravitational forces are squared and things like that. So I have a nonlinear differential equation for the position of my spacecraft or asteroid in this potential well. And there are 5 fixed points. There's one like right here, right here, right here, about here, and here. I probably butchered the actual placement, but there's 5 fixed points in the plane. This one's pretty obvious. If I'm exactly equidistant between, I should probably draw this correctly. It's way over here, right? I have to be closer to Jupiter to be equal gravity. So if I'm at exactly the neutral gravity point, where the sun and Jupiter are pulling equally on me, I'm not going to move, right? Like, I'm going to stay there forever. No one's winning. There's also rotation. So there's also a point here where I'm being kind of thrown away from the sun as much as the sun is pulling me towards it. And another point here on Jupiter where I'm being thrown away from Jupiter as much as I'm being pulled towards it. And then these are also fixed points. We're in a rotating frame. It doesn't make intuitive sense to me. Okay. You asked for a physical explanation of where saddle points really come into play. So if I have a potential, if I write down the gravitational potential, if I am an asteroid and I only have so much energy, then there are only certain regions of this space where I can live. How do I draw the opposite of this? So I can't, these are energetically forbidden regions where I don't have enough energy, right? So let's say I'm a fast asteroid, but I'm not super fast. Then I can't get to any of these blue regions from the outer solar system, okay? I have to come through this opening to get into the inner solar system. They proved this about 10 years ago, okay? Like at Caltech and at JPL, they showed that these 2 fixed points mediate the transport of asteroids and space junk into the inner solar system. So we're actually, and these points, if I linearize these fixed points, there would be 2 stable directions and 1 unstable direction. So if I was perfectly along the stable eigenvector, there are things called halo orbits, where I would stay in a perfect, beautiful halo orbit around this point forever. But if I get just a little bit nudged, I unwind from that halo orbit, and I either go to the outer solar system or I go to the inner solar system. Okay, so these saddle points actually protect us from space junk. So the Sun, Jupiter saddle points protect us from asteroids and comets, and they also give us energy-efficient ways of getting very, very far away. So if I'm at one of these fixed points and I give myself a little nudge in the unstable eigenvector direction, I get carried off forever in that direction, or at least until I get picked up by another object. So the Hubble Space Telescope was one of the coolest things that came out when I was a kid. You could see pictures of, all of these great, things. And the next generation Hubble is called the James Webb Space Telescope, and they're putting it in one of these saddle points in the Earth-Moon system. Okay, they put it in that saddle point because it's cheap to get there and it's easy to maneuver because it has an unstable direction. Okay. A person walking is a saddle point. Okay, my arms are stable. If I just start my arms and I let them go, they damp out and they stay in the vicinity of where they started. They're stable. But my whole torso and body is an unstable direction, right? I'm an inverted, unstable pendulum. So if I go a little bit this way, I have to keep going that way. And so when I'm walking, I have one stable direction, my arms, and I have one unstable direction, which is my whole body. Okay, and having that little unstable direction makes it so that I can propel myself extremely efficiently forward by just nudging myself off in the unstable direction. I just go a little epsilon unstable, and I move in one or the other directions. Okay, this is so you got me on one of my favorite topics. I love saddle points. I love that they look like saddles. You can use them for energy-efficient orbits of moons, of Jupiter. I'm going to talk about this later. So when I get into the lecture in about a week or two on chaos, we'll find that these systems, not this one, but if I added one more body, it would be extremely chaotic. And these saddle points give us some order in the chaos. They define kind of islands of regularity in a sea of chaos. Okay, that was a long segue. So if I wanted my saddle to be rotated 45 degrees, how would I do that? Right, so I would essentially assume that I had some eigenvectors like the ones that I wrote down in the previous system that were at 45-degree angles. And I would just take that t, 1, 1, 1, negative 1, times my original a, which is 1, 0, minus 1, 1, times t inverse, 0.5, 0.5, 0.5, minus 0.5. And I would call that my new A matrix. If I wanted an A matrix where my saddle was rotated 45 degrees, I would just create something that rotated it by 45 degrees, and I would multiply by t and t inverse. And I think that this would still look like that now. So I'd have an unstable direction. And now I would have a stable direction. And my initial conditions are still going to go in these kind of like this. Okay. Pretty simple. So you can rotate these. You can, on the homeworks, right? I want a certain system that looks a certain way. I just cook up a diagonal matrix with the right eigenvalues, and then I make my T to make it look a certain way. Okay, so a couple more examples. We have maybe 5 more minutes. Okay, I didn't get as far as I wanted. Let's see. Okay, so the next example that we're going to do is where things get really interesting. And this is a good place to leave off for the next lecture, because this is something that we should all think about a little bit before jumping in. So for the final example, we're going to have a system like x dot v dot equals 0, 2, minus 2, 0 times xv. Okay, very similar to the saddle, except it's not. Right? Instead of having these on the diagonal, they're on the off diagonal. And that subtle difference makes a really, really big difference. Okay, so what are the eigenvalues of this system? A minus lambda I equals minus lambda 2 minus lambda. So the determinant of A minus lambda I is what? Lambda squared minus 4 is plus 4. Okay, so that means lambda squared equals minus 4, and lambda equals plus or minus 2i. Okay, this is just like the undamped spring mass system that we saw, right? I had x double dot plus 4x equals 0. Well, it's a little different, but it's basically the same equations. It has the same eigenvalues. So it has the same eigenvalues as the undamped spring system. What does that system do? If I just have a mass on a spring with no damping and I let it go, what does it do? Oscillates forever. So we have some idea that this solution should oscillate forever. Okay? But this is interesting, right? Now my eigenvalues are imaginary. So e to the 2it has an imaginary part, and so does e to the minus 2it. So what we're going to do is find the eigenvectors of this matrix for each of these eigenvalues. We're going to construct a T matrix, T e to the dt, T inverse. We're going to solve our system like this, like we have for everything. And what we're going to find is, this is a real valued A matrix, right? And my spring and mass have real positions and real velocities. So my solution had better only have real parts. Okay, so when you actually compute the eigenvectors and the inverse of the eigenvectors and e to the lambda t, all of the imaginary parts cancel out. Okay, I kind of gave away the ending. But what happens is, when you actually do this by hand, we're going to find that all of the imaginary parts of this completely cancel out, and what we're left is with a real valued solution matrix, which is what you expect, right? E to a real numbered matrix should be a real number matrix. Okay, so I would like you to think about this problem and start, think about how you would compute the eigenvectors for this system. We'll work it all out on Wednesday. Okay, thank you.